Welcome back to another session of carbon and its compound. In my previous session, I have already explained the chapter up to the topic compounds of carbon. In today's session, I will be explaining soaps and detergent. It is one of the very important topic of class 10th and every year questions are asked from this topic. So let's begin today's session. Now, first of all, we will try to understand the basic information about soap and detergent. As you all know, soaps and detergents are the cleaning agents. These are the cleaning agents. They are used in every household and they give us the cleansing action. If you see chemically soaps are sodium or potassium salts of long chain carboxylic acids. If you can recall, carboxylic acid is a functional group COOH, or it can be written as C double bond O, OH on the one side, and here is the hydrocarbon tail R. So R is what? R is hydrocarbon tail. So this COOH group is present in the case of the soaps, but they are the salts of the potassium or the sodium. These are salts of sodium or potassium. Okay. Now, if you see the general formula of the soap general formula is RCOONA. Okay, so R, you know that it is the hydrocarbon side. COO is what? This COO here, and this H, when in a chemical reaction, this H, that H plus ion, cation, gets replaced with another positive ion cation. It can be sodium or it can be potassium. Then it changes to soap. Then you will get the formula RCOONA or RCOOK. Now this hydrocarbon chain is very long. Okay, it can have up to carbon 17 H35. It can have carbon 15 H31, or it can even have carbon 18, carbon 19, 20, 21, 22 and so on. So this is the general formula of the soap, RCOONA, or you can write K. So if we will try to write formula of any simple soap, we can use this hydrocarbon C17H35 and COONA. Similarly, you can write with potassium C17H35 COOK. If you want to write with the 15 one, C15H31 COONA, then C15H31 COOK. So these are some formula of the simple soaps. Now let us see the detergents. Detergents are ammonium or sulfonate salts of long chain hydrocarbon. That is, they are having a general formula. Detergent, if you see detergents, they are having a general formula of R, which is the hydrocarbon, then SO3 sulfonate group and Na here. Okay, so R is again the hydrocarbon chain and it is also long in this case. Same, it will have the carbon 17 H35, it can have carbon 15 H31 and so on. So the hydrocarbon chain in both the cases is very long actually. So this is some general information about the soaps and detergent. Now let us try to see that how the soaps and detergents are made. So we will be understanding the manufacturing of soaps and detergents. See, soaps are basically the animal fat or the vegetable oils when they are heated with sodium hydroxide. It is an alkali also. You are knowing by this time from your previous classes or from the previous chapters you are knowing. And since this reaction involved formation of soap, so it is also called as saponification reaction. Now this is a general way in which I have explained the same lines. Fat or oil plus alkali will give us soap and glycerol. Now if you see the fat or oil here, you can use simple ester, which we have understood in my previous session, or you can write simply like this: CH2O, C double bond O, C17H35. You can take one molecule or more than one even in this case. So I am writing CHO, C double bond O, C17H35, CH2 again, O, C double bond O, C17H35. So when it will react with alkali, here it is NaOH, this alkali which is written, I am writing it here as NaOH, will give us soap plus glycerol. Okay, so this is an ester molecule. There are 3, 1, 2, 3, so I can write it as triester also. Okay, now see, when this reaction will occur, what will happen? This whole side from here it will get broken. Okay, it will dissociate. Okay, so this will become negative and this will become positive. Similarly, NaOH, it will break into two parts. This will become positive, Na plus cation and OH minus anion. Now opposite charges attract, you know. So what will happen here, that this Na, the Na will go to this side, O, it will attach itself to O, and this OH will be attaching itself with CH2, CH2 side here. Okay, so now here there are 3 molecules of, there are 3 esters here, so you can write here as 3 NaOH. So now 3 Na will be there, so you can write simply as C17H35 COONA. Okay, these are 3 here, so we will be writing 317H35 COONA, and then plus you can write this side will be changed to the glycerol. CH2 will get OH here, then CHOH, and then CH2OH. Okay, so this will be the glycerol and this is the soap. Okay, so this whole side here, CH2, CH, CH2, I have copied as such here, and the OH which is coming here, 3 OH will be coming, so they will be attaching itself with each carbon here, C, C and C. Okay, so this is the formula 3C17H35COONA. Right, so in this manner the soap are obtained. This is one example, one very simple example. We can have more, like very long chain here also, the alkyl group you can change. Now if we will try to understand the soap. Okay, soap is what? If we see soap molecule, the soap molecule has got 2 different parts having 2 different properties. Every soap molecule is having 2 parts and each part is having different property. Okay, now you know that the basic formula is RCOONA, right? This COO will have minus charge and Na will have the positive charge. Here you will be having the negative charge and this Na is the positive, right? So this is the general formula of the soap. So now this whole molecule, that this R is what? This is the hydrocarbon chain or the tail, right? Now if you see the picture here, this whole thing here is the hydrocarbon part from here to here. This is the R, this is the R, and this is COO and this is Na, right? So this is the one soap molecule, RCOONA. So you can see that R, which is the hydrocarbon, it is a very long chain. It is a very long chain. Okay, and this is called a soap molecule and its chemical name is sodium citrate. Now if you observe this one here, RCOO minus Na plus, then you can see that this is a very short ionic end. This is a very short ionic end here. Okay, this is a very short ionic end here. It is having the charge to it, okay, negative charge to it. So this is the ionic end here. On the other hand, R is what? It is the hydrocarbon chain. It is the hydrocarbon chain, okay, and it is not having any charge. There is no charge on it. There is no charge. But here it is the ionic end and it is having charge, right? when the soap will be dissolved, this Na will go out itself. Okay, so what will be here? We will have only the part RCOO minus here. Okay, that is this Na. If you see in this picture, Na will go out and we will be having only RCOONA together with this negative charge. Okay, and Na will be away somewhere in the water. So now this RCOO minus, so R is what? R is a hydrocarbon chain which is shown by this upside down line, and at the end of it there is COO minus. So this is the ionic part. Now this is the ionic part, it is having the charge to it, right? And this whole thing is the hydrocarbon part here. This is the hydrocarbon chain, that is the R. It is not having any charge, there is no charge. So if there is no charge, then this is non-polar end. This is called non-polar end. Okay, so this whole side is called as non-polar end. This is non-polar end here. But this head is having charge, COO minus, it is having charge, so it is called as the polar end. Okay, now this is having charge to it, it is having the ionic charge to it, right? So this ionic charge means that it is having some charge to it which is here negative. So if you will dissolve the soap molecule in water, then what will happen? If you recall, water is HOOH or H2OH in short we call it, and HOH always dissociate in H plus ion and OH minus ion, right? So it is an ionic, it is also having the ions in it. Okay, H plus and OH minus. So I am writing here, so it is H and OH minus, right? So what will happen? If you will dissolve the soap in the water, then the head which is ionic here, this is the ionic side or the ionic end, this ionic end will dissolve in water. Why? Because water is also ionic compound. In science or in chemistry, what we say that like dissolves in like. We always say here that like dissolves in like. That is the one, they always dissolved in alike things or the substances. So if it is an ionic compound, it will dissolve in an ionic compound. So this ionic end will get dissolved. It will get dissolved in ionic compound like water. But this hydrocarbon part, which is a non-polar part, is not having any charge. You can see this picture, it is not having any charge to it. So it will not dissolve in water. It will not dissolve in water. But it will dissolve in organic solvent like them. It can dissolve in organic solvents like them. Organic solvents will also have the carbon and hydrogen chain, hydrocarbon chain they will have. So obviously they will dissolve itself in the hydrocarbon or the organic compounds. Okay, so if you see this side is ionic side, COO minus side is the ionic side, so it is also called as a polar end and it gets dissolved in water. On the other hand, the non-polar end is the hydrocarbon part because it is not having any charge to it, and since it is a non-polar end, it is not having any charge to it, so it will dissolve itself in organic solvents only and not in water. Now coming back to the notes here, a long hydrocarbon tail. So by this time you are knowing that there is a long hydrocarbon tail which is shown by this zigzag line. This is non-polar, that is it is not having any charge. So it is not having any charge, so that is it is not an ionic compound, so it will be insoluble in water. And since it is insoluble in water, so it is also called as hydrophobic tail. Hydrophobic tail means, hydro means water and phobia means that you are scared of it. So obviously it will never dissolve itself in the water, so it is also called as a hydrophobic tail. But on the other hand, the end of the soap molecule which is having charge to it, it is the part which is polar, that is, it is charged. Since it is charged or it is having ion to it, so it is soluble in water, and therefore it is called as a hydrophilic head, that is the water loving end. It is a water loving end. Okay, so in this way every soap is having two parts. One is the non-polar part, another one is the polar part. The polar part is having charge, so it will dissolve itself in something which is charged, that is in the ionic compound like water. Okay, water is an ionic compound. On the other hand, the hydrocarbon tail, which is the non-polar end, it will not have any charge, that is why the name is non-polar. So it will dissolve itself in some organic solvent but not in water. Now let us try to understand the cleansing action of the soap after understanding the structure of the soap. Now if you see the cleansing action of the soap, now see, when you are putting soap into the water, let us say that there is a bucket or a tub which is having water to it up to this level. Okay, this is water here. So when you are putting water in a bucket and you are adding soap to it, so what will happen? When the soap molecule will lie on the surface, then their hydrophilic end will be towards water, and the hydrocarbon tail, that is the tail which is non-polar, will be away from the water, because hydrocarbon tail will not get dissolved in water. It is not a water loving end, so it will be away from the water. But the head, which is hydrophilic or the charged head, the polar head, will be towards the water, and this hydrocarbon chain, which is non-polar, it will be away from the water. Okay, so the same thing is written here, that when soap is at the surface of water, non-polar hydrophobic hydrocarbon chain will not dissolve itself in the water, and the soap molecules will align along the surface of water with their polar hydrophilic heads in water, and the non-polar hydrophobic hydrocarbon tail will be out of water. It will be coming out of the water. But when it will be mixed, that is, the soap will be mixed in water properly, then what will happen? After mixing, see, inside water there are the soap molecules like this, ionic end and the non-polar end, right? This is the ionic end, it is having negative charges to it. Okay, so it will be inside water, okay, moving. Now what will happen? It is having negative charge, it is also having negative charge, it is also having negative charge, it will also having negative charge, it will also having negative charge. So you know that the same charges ripple, that is, they will move away. Okay, they will move away from each other. So if they will move away from each other, then what will happen? They will align itself like this. The head will never come close to each other because they all are negatively charged. They all are negatively charged. Okay, so at last what will be the structure? The negative charges will be away from each other and they will be surrounded everywhere along with water molecule. Okay, they are inside water, but the tail is not having any charge, so they will be coming together. Okay, but the head will be always away from each other. So it will ultimately give rise to a spherical structure, a spherical ionic structure, a spherical ionic structure. And if you see the structure here also, everywhere in the surrounding the water molecules are there. This is the hydrophilic end which is having negative charge to it. This is having negative charge. So they are away from each other, but the tail is not having any charge. There is no charge here, right? So they will be together, like they will be inside, or they can touch each other, they can join with each other, but they will not be away from each other. Hydrophobic tail. So what will be there that inside water we will be seeing the formation of the spherical ionic structure, and these spherical ionic structure are also called as micelle. So micelles are what? These are the bubble kind of structures, the small foam which you see. Inside the foam there are a lot of micelles basically. So now after this, what we will be seeing that inside the water, the polar hydrophobic heads of the soap molecule dissolves in water, and the non-polar hydrophobic tail dissolve in each other, leading to the formation of the spherical ionic micelle. Okay, this is also a structure of a micelle. So these micelles remain inside water and they form a colloidal solution. They form a colloidal solution. Okay, and they do not come out together or they precipitate out because there is a repulsion between the similar negative charges. So this much we have already understood. Now inside water, after the formation of the micelle, you know that it is having the head which is away from each other and the hydrocarbon tail is towards each other. Okay, like this I am drawing here. So these are the negative charges. Now see, these are the negative charges, or the negative heads are hydrophilic or water loving, so they will be having the water molecule, or they will dissolve itself in the water molecule. But the hydrocarbon tail will not dissolve itself in the water molecule. Instead it will be attaching itself to the oil or the dirt. Oil, dirt, or you can also say grease or fat, anything like that. So whatever is there, fat, grease, oil, dirt, whatever is there, the tail will attach itself to the fat, grease or oil. Now why? See, the tail is made up of hydrocarbon which is organic. Okay. Now it is not having any charge also, there is no charge. So what will happen? The fat, grease, oil and dirt, they are also organic in nature, they are also not having any charge. So like dissolves in like again. So this is the organic side, it is not having any charge, so it will dissolve itself with fat, grease, oil or dirt. So it will be sticking to the oil, dirt, grease, fat, whether this oil, dirt, grease, fat is on your cloth or on any surface, or it is on your skin, wherever it is. So it is always the hydrocarbon tail or the hydrophobic end which is over to the dirt or the fat, oil or grease, and the head will be towards the water. So after this, what will happen? See, now by this time micelle is formed, and at the center of it, it is like the hydrocarbon chain is already attached to the fat, grease, oil or dirt. Now we need to break it so that the oil and dirt can be lifted out or taken out. Now how this breaking can be done? Either it can be done by using a mechanical scrubber, which can be a brush. So we can use a brush over to the cloth, or you can beat it with a wooden paddle, or you can beat the cloth itself on a small stone, or it can be agitated inside a washing machine. That is the rubbing and the scrubbing action which goes inside the washing machine, that is called as agitation, the constant rubbing of the cloth inside the washing machine. So in this way what will happen? We are giving a force, we are applying some force so that the organic end or the hydrocarbon tail can take the oil, dirt or grease along with it. Okay, it will get broken. So what will happen at the end of this process? First of all, the oil and dirt particle will be loosened and then they will be removed from the cloth itself. So this is the cleansing action of the soap, and at the end we just wash it off with the plain water. Now coming to the very small but a very important topic between hard and soft water. Now see, we have already understood about the soaps and detergents, but there one difference I have not told you. Okay, the soap, they work well in the soft water, and the detergents also work very well in the soft water. Okay, but in the hard water only detergents work. Okay, no soap works in case of the hard water. Why is it so? Because the hard water is actually having the salts of magnesium and calcium in it. Okay, magnesium, you can take example like MgSO4, it can have calcium also, CaCl2. Okay, so these are the salts which might be there, and because of that the soaps are not able to perform well inside the hard water. Why is it so? Because whenever the soaps are used in hard water, whenever the soaps are used in the hard water, whenever the soap are used or applied in hard water, there is a formation of the scum. That is the curdling precipitate which you have seen. Okay, that is called as the scum. Now here, in case of the soap, what happens that, let us take for example C17H35COONA. This is the formula of the soap plus hard water. So hard water is having the salt in it. Let us say we are taking CaCl2 salt. So when they are mixed together, that is, this is the hard water which is having the salt. I'll write here hard water containing calcium salts. Okay, so the Na is a positive side, so Na will get replaced, this Na will get replaced with calcium ion. Calcium ion, it will get replaced and it will form a new compound C17H35COOCA. Okay, so this is the actual scum. This we see in the form of the precipitate which comes out here. I'll put 2 here and this will not come here. Why it is 2 here? Because calcium valency is 2, remember. So you know that the valency always goes to its neighbor, so it is 2, and it will be C17H35COO whole twice Ca. So this is the formula of the scum. So this is what we see as the curdling precipitate which comes out, and it usually gets stick over to the cloth or to the surface itself. So basically they are not able to work well, the soaps are not able to work well because the hard water contains the magnesium and the calcium salt, be it is a chloride or it can be a sulfate or it can be a bicarbonate salt of calcium or magnesium. At the end of it, we always see that it will form scum. Scum is a curdling white precipitate which stick to the cloth or to the surface. So at the end of this session, we have finished the chapter carbon and its compound, and in my next video I will be doing a Q&A over the chapter carbon and its compound. But before going, I would like to request you all again to kindly subscribe to my channel and keep showering your love. Thank you.